Hello, everybody. Welcome back. Today we're going to be looking at Unit 4.7, which is all about the different types of chemical reactions. So let's get started. We're going to be looking at 3 different types of reactions today, the first of which is acid-base reactions, which also can be called neutralization reactions. And this is just an example of one in front of you here, very simple example. And if you remember back from your Chem 1 class, you likely learned that many acid-base reactions will produce a salt, meaning an ionic compound, and water. Okay, now we're going to learn that they don't always produce that, but many of them do. Okay. And if we were to take an example like this one, and I said to you, please write out the net ionic equation, you would use your solubility rules. And this particular reaction would come out looking like this in terms of the net ionic. All right, because if you guys will recall from your solubility rules, you have a rule that involves strong acids and strong bases, and we would find that both the acid and the base in this particular reaction would dissociate, ionize, and this is what we would be left with. And in fact, if you are dealing with a strong acid added to a strong base, this is in fact the net ionic equation that you will always end up with. Okay, now as I said, this example in front of you is kind of more of a simpler acid-base reaction, probably more of the type you would see in Chem 1. And I'm gonna show you a little bit more complex ones of what it looks like more in an AP kind of setting. And actually our next unit, Unit 4.8, is going to go into even more detail in terms of acid-base reactions. So let's talk a little bit of vocabulary and make sure we understand how to recognize a compound as an acid and a compound as a base. In your Chem 1 class, you likely learned something called the Arrhenius concept, which essentially says that acids are compounds that begin with H+ or hydrogen. Bases are compounds that end with hydroxide. Okay, the more formal definition is acids produce hydrogen ions, bases produce hydroxide ions. And it's not that that concept is wrong, it's just not quite complete, especially when it comes to bases. For example, ammonia, NH3, is a base. But if you look at the formula, it doesn't even have hydroxide in it. So according to the Arrhenius concept, that wouldn't be a base, but ammonia is definitely a base. It's definitely a basic compound. So there's a newer model called the Bronsted-Lowry model of acids and bases. And the acid definition isn't that different, but the base definition is quite different. So the Bronsted-Lowry definition for acids says that they are hydrogen ion donors. These are the compounds, the reactants that are going to give away a hydrogen ion, or it'll look like they have lost a hydrogen ion. And before I talk about bases, on occasion, you will see Bronsted-Lowry acids defined as proton donors. And I want to explain why that word proton is in there. If you think about what a hydrogen ion really is, it's a particle that has 1 proton, 0 neutrons, and because it has a +1 charge, it's lost, that hydrogen has lost the 1 electron that it did have, so it doesn't have any electrons either. A hydrogen ion is really nothing more than just a proton. Have I blown your minds? Okay. So sometimes acids are defined as proton donors, and thus bases will be defined as proton acceptors, the compound that takes on or accepts that hydrogen ion. So if you look at this example in front of you, all right, you probably could pick out that HCl is the acid right away. You're familiar with hydrochloric acid. And look at what's happening to it from left to right, from reactant to product. It is giving away its hydrogen ion and becoming Cl minus. That's no big deal, but look at what's happening to water. Where is that hydrogen going that HCl gave up? Water is accepting it. So as weird as it sounds to say this, water is the base, the Bronsted-Lowry base in this example. So when you are asked to recognize, is this, or answer the question, is this reaction an acid-base reaction? You're looking for, was there a transfer of a hydrogen ion from one reactant to another? That is how you recognize an acid-base reaction. And as I said, we're going to go into a lot more detail in that in Unit 4.8. The second type of reaction is called a redox reaction. That term redox is a shortening of the words reduction and oxidation, which should be familiar to you from Chem 1. So let's review a little bit of vocabulary here. And I have a mnemonic device for you. Okay, Leo the lion says grr. Lions don't say roar, they say grr. It's a fact, look it up. Okay, and these letters stand for something. Whichever element has lost electrons is the element that has been oxidized. Whichever element has gained electrons is the element that has been reduced. So a redox reaction, ladies and gentlemen, involves a transfer of electrons from one element to another. So instead of, like in an acid base, instead of transferring a hydrogen ion, we're transferring electrons. And how are you supposed to know which element has lost electrons or gained electrons? Well, we're going to use this example in front of us. We are going to assign what are called oxidation states. Oxidation state is just a fancy word that means charge. We're going to write the oxidation states above each element. So when oxygen is in an ionic compound, it's always -2, which means this iron must be +3. Aluminum, elements by themselves have oxidation states of 0. Here's another one. Oxygen is again -2, which means this aluminum is +3. And now we're going to look at each element individually from left to right. What's happening to it? So iron is going from a +3 oxidation state down to 0. Its charge has decreased. You know what's a synonym for the word decrease? Reduce. Iron has been reduced. How did that happen? It must have gained electrons. Okay, oxygen is not changing at all. Aluminum has gone from 0 to +3. Its charge has increased, so it must have been oxidized. How did it increase? Because it must have lost electrons. So you'll notice, guys, you have to have one of each. all right? If you have one element that's been reduced, you must have another element that's been oxidized, okay? These are called REDOX reactions. They're not called read or ox-ox. You have to have one of each. Now, you might be wondering, how did I know what those charges were going to be? How did I know how to assign those oxidation states? And there are rules for this, most of which are probably common sense to you. For example, we said that an element that's written by itself has an oxidation state of 0. Okay. Sometimes you will see ions written into an equation and the charge will be written right next to it. And in that case, that's really nice. You don't have to guess what its oxidation state. It is the charge that's written right next to it. All right. As we said, oxygen in most compounds, ladies and gentlemen, most of the time, oxygen is going to carry a charge of -2. There are exceptions in compounds that are called peroxides, where it carries a -1 charge, but that's pretty rare. If we're looking at a covalent compound, hydrogen's always going to carry a +1 charge. And if you're looking at a neutral compound that has an overall charge of 0, you can use that fact to figure out some of the unknown compounds and figure out what their charges are. Let's say instead of a neutral compound, you're dealing with a polyatomic ion like sulfate. We can use what we know about oxygen to figure out the charge of sulfur. So oxygen's going to carry a -2 charge. That's -8. Okay, -8 plus what has an overall charge of -2. So that means sulfur's oxidation state must be +6. So that's what I mean by you can use the oxidation states of the elements that you know to figure out the ones that you don't know. Okay, so this is what I would like for you all to do. Should be very quick. I just want you to pause your video and write the oxidation states above each element, and then we'll check it. All right, let's see how you did. That last one is a little weird. Okay. Now, I'll tell you, Fe3O4 is a compound that does exist, okay? I mostly just put this here as an example to show you, to make sure that you all understood the math of how to figure out the oxidation state of some kind of unknown element. So we know oxygen is -2. That means the iron in this case must carry a charge of +8/3, which is very bizarre, I understand. All right, so just to make sure that you've got this, okay, let's say you have a really simple example here. We're going to assign oxidation states, and we look at what is happening to each element from left to right. Ask yourself, has that element lost electrons or has it gained electrons? So what I would like for you to do in each of these examples is to identify what substance has been oxidized, what substance has been reduced. Remember, the easiest way to do that is to assign oxidation states above each element. So I want you to pause your video and try it. All right, let's see how you did. So I've written all of the oxidation states in green, and then I've identified what element was oxidized, what element was reduced in yellow. And just want to call your attention to one thing right down here, okay? Just an example of sometimes when an ion is written into a reaction and the charge is given. You don't have to guess about what the oxidation state is because it's written right there. But if it just said Mn and there was no +2 next to it, then it would have an oxidation state of 0. Okay, so sometimes you see ions, sometimes you don't. But if it is an ion, they will give you the charge. Third and final type of reaction, ladies and gentlemen, is called a precipitation reaction, where you combine two aqueous solutions and they create a solid product, okay? And this is just an example. This is the reaction between potassium iodide and lead nitrate, and this is really what it looks like, okay? Lead iodide is a bright mustardy yellow solid product. And the reason that you get a solid product is because that compound is insoluble. If you look at our solubility rules, it says halide salts, most of them are soluble, but some exceptions involve those when it's linked to lead. And there would be the net ionic equation. So the way you recognize a precipitation reaction is you're looking for a solid product. So let's look at an example here. It says, looking at the reactions below, identify each as an acid-base, a redox, or a precipitation reaction. So if you want to pause the video here, you can and answer these yourselves. Otherwise, I'm going to go ahead and talk through it. So looking at that first one, the thing that jumps out at me is I see a solid product. So that is definitely a precipitation reaction. It's not acid-base. There isn't even any hydrogen in that reaction. And if you wrote out the charges of all the elements, you would see that nobody is changing charges there. So it's definitely just a precipitation reaction. The middle one, if you move your eyes from left to right, okay, and let's just take one reactant at a time. If you move your eyes from this guy to what he becomes, what has happened? That ion on the left has accepted a hydrogen ion. And where did it come from? It came from the other reactant. Remember, the definition of an acid-base reaction is a transfer of a hydrogen ion, and that's exactly what has happened here. So it definitely is acid-base. There's no solid product. It's not a precipitation. And again, if you wrote out the oxidation states above each element, you would see that they are remaining unchanged. Last one. There's no solid product, okay? I don't see a hydrogen ion being transferred. So it must be a redox, but I want to prove it to you. And I'm going to do that by writing the oxidation states above each element. So hydrogen is going to be +1. That means that this particular carbon, must carry a -1 charge. I know that's a little bit unusual, but carbon can carry a variety of oxidation states. Oxygen here is 0. When it's in a compound, this oxygen is -2. That means this carbon must be +4. Oxygen is -2. Hydrogen is +1. So I can see that carbon has been oxidized, and I can see that the oxygen has been reduced from left to right. So this is definitely a redox. You'll see questions like this frequently in multiple choice. So that was just going over, how do you recognize the different types of reactions? And I hope you've learned a little something today, and I look forward to seeing you next time.